Good day, Math 30-1s. Today we are expanding on the idea of permutations and combinations into something called the binomial theorem. So the point of today is to be able to expand something like 2x minus 3y squared all to the power of something crazy like 8. A task that seems quite complex and can be simplified using something called the binomial theorem. So we begin today with Pascal's triangle, a bit of a strange pattern that results from a bit of a connection between something that could be created using a bean machine or a modified version of Plinko. But essentially the idea is that we've got a whole bunch of ones down the outside, and we can use a little bit of addition to generate the numbers on the inside. So starting with these ones here, if we add those together, they can come together to make a 2. This 2 and the 1 could come together to make a 3, and as we continue this pattern, we could see that a 3 and a 1 would make a 4, 3 and a 3 makes a 6, 1 and a 3 makes a 4, and again a 1 on the outside completes this row. You could probably try to figure out the next one on your own, but it would be a 1, 5, 10, 10, 5, and a 1. And you might notice a few patterns in here. The most common ones might involve simply that there's an increasing and then decreasing arrangement of the same numbers, a palindrome of sorts. So we've got this triangle called Pascal's triangle, and embedded in it is quite a bit of helpful logic. So a couple of questions just to talk about some of the patterns in here. What is the sum of each row? In the very first row, there is one number, so its sum is 1. The sum is 1 plus 1. The sum is 2 plus 1 plus 1, 3 plus 3 plus 1 plus 1. And you'll see there is a bit of a pattern here in even the sum. 1, 2, 4, 8, 16, 32, and so on. It seems like there is a base 2, or 2 to the power of something that results. Now this is a 2 to the power of 0. This is a 2 to the power of 1. And if I compare that to the row number, in the second row it's 2 to the power of 1. So if we actually just write a little formula, 2 to the power of row minus 1, 2 to the power of 3 minus 1, row minus 1, we get 2 squared. So there's a little bit of a pattern that tells us if we take the row and subtract row number and subtract 1, we can generate the sum. So I could ask, what is the sum of the 10th row? And we would say 2 to the 9 and get our sum. Determine the sum of each row. We'll just write in a little bit of a formula, 2 to the row minus 1. And this can be generated simply by looking at the first few rows of Pascal's triangle, looking at the sum, and making that formula again if you needed. So what is the sum of the coefficients in the 12th row of Pascal's triangle? We could say 2 to the power of 12 minus 1, and quite quickly we've got our calculator. 2 to the power of 12 minus 1, 2048 results. Amongst other patterns, Pascal's triangle can actually be created in a slightly different way that we've seen before. When we examined pathways questions, we had not just talked about the number of rows and columns generating our answer. We actually examined these pathways problems by looking at maybe from an A to a B using a counting method. We may have said there's one way to get here and one way to get here and one way to get here if we're just traveling straight across. There's one way to get here and here and here and here. And if we look at this, 1 and a 1 making a 2, 2 and a 1 making a 3, 1 and a 3 making a 4, 4 and a 1 making a 5, 2 and a 1, 3, and keep this adding process going. 1 and a 3 is a 4, 6 and a 4, 10. We seem to generate, and I'll pause here for a moment. We seem to have, if we turn this 45 degrees to the side, we actually have Pascal's triangle. 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 5, 10, 5, 1, with the one that would be here if this pathways question was larger. ultimately, there is Pascal's triangle embedded in this type of logic. For a question like this, we would have approached it by saying there is 1, 2, 3, 4 rows, and there is 1, 2, 3, 4, 5 columns. And so we could have said this is a 9 factorial divided by a 4 factorial, 5 factorial. Mathematically, this works out exactly the same as an n factorial over r factorial n minus r factorial. They look very, very similar. This is a combination in the form of 9c4 or a 9c5. So mathematically, I could determine the number of ways to get to here, or the value in this location, by computing 9c4. And there's a deep connection between that location and expanding a binomial. And so we're going to explore this idea of how combinations can help us build specific parts or individual locations in Pascal's triangle, and then perhaps build on the actual expansion from start to finish. So let's try to connect a few dots and talk about this expansion of a binomial, about Pascal's triangle, and about these combinations. So when you expand and simplify a binomial, we're going to write some coefficients of the expansion on the left and compare these to what results. So if I were to talk about x plus y to the power of 0, the hope is that we could expand this and say, well, anything to the power of 0 is a 1. X plus y to the power of 1 means nothing is actually newly created, and so our coefficients are a 1 and a 1. In the expansion of x plus y squared, we would generate an x squared plus a 2xy plus a y squared, and those are your coefficients. In the expansion of x plus y cubed, you're more than welcome to give it a try, but you would end up with a 1 x cubed, a 3 x squared y, a 3xy squared, and a y cubed. Continuing this pattern produces Pascal's triangle. A 1, 2, 1, 1, 3, 3, 1, and of course, if we were to expand this to the power of 4, 5, 6, 7, every row of Pascal's triangle would simply produce the coefficients. Now, a little bit new, as combinations, I can generate any one of these locations by using a combination. In fact, 0c0 creates a value of 1. 1c0 creates a value of 1. 1c1 creates a value of 1. 2c0 creates a 1. 2c1 creates a 2. And a 2c2 creates a 1. So what's happening here is there's a very, very nice connection between the power on our expansion, and I'll pick on this power of 2, and the first number in our combination, and what we select as our r can help generate the first location, second location, third location, or first term, second term, third term. The most tricky part about this is that for the first term, we're choosing 0. For the second term, we're choosing 1. And for the third term, we're choosing 2. And I'll talk about this offset selection a little bit later. But combinations are going to help us create Pascal's triangle, which are also going to help us create the expansion of a binomial. And everything is interconnected. So let's outline the idea in one nice visual that we're going to be used to help us out going forward. So I've got the first 5 levels of Pascal's triangle and the corresponding combinations. Pascal's triangle in the middle, the binomial on the left, and our combinations which create Pascal's triangle in the middle here. So these are going to help us to expand something a little bit more complex than p plus q to the power of 5, but we're going to start with this. So p plus q to the power of 5 implies I'm asking you to expand p plus q plus p times p plus q times p plus q times p plus q times p plus q 5 times. Now think of all the arrows that would be created to make this possible. Certainly a bit more work than we'd like to do. So in the expansion of p plus q to the power of 5, I can consider the next row here, the sixth row in Pascal's triangle, which is x plus y to the power of 5, as having coefficients 1, 4 plus 1 is a 5, 10, 10, 5, 1. I'm not going to jump into the combination values yet, but I'll start with Pascal's triangle. So if I know that the coefficients of this expansion should be a 1, 5, 10, 10, 5, and a 1, all that's left is to place in the p's and the q's. I know that when this is expanded, the p and the p and the p and the p and the p are at some point going to create a p to the 5. That's our very, very first leading power. Our very, very last term should be a creation of a q and a q and a q and a q, 5 q's. What's very, very impressive and convenient is that as we expand this, we have this descending power of the p. After the 5 becomes a 4, and then a 3, and then a 2, and then a 1, and then there's no p's left. There's either an ascending, or as I work maybe from the right, a descending power of q. It's a q to the 5 on the right, a q to the 4, and then a q to the 3, a q squared, a q, and then a q to the 0, which we'll leave out. These are the 6 terms in the expansion of p plus q to the power of 5. Done. Pause for dramatic effect. Because we're using Pascal's triangle, not arrows, not distribution, we're using Pascal's triangle and a simple pattern of descending and ascending coefficients to build this. This would be your final answer. A very powerful tool that we're still just scratching the surface of what we're able to do. So as we flip it over, we have a few questions to analyze with this. How many terms were in the expansion of p plus q to the power of 5? What you may have noticed, and you're welcome to flip back or to rewind, we have 6 terms in the expansion. And as you might notice, to the power of 0 had 1 term. To the power of 1 had 2. Squaring had 3 terms. There's always one more term than the power we're expanding. There is always one more term than the power we're expanding. So the number of terms, we make ourselves a little formula, the number of terms is equal to your power plus 1. So in this case, how many terms would exist in the expansion of something to the 8? 8 plus 1, there would be 9 terms. So very specifically, we're going to now try to get into the use of combinations and how this right side can help us out. So here's another visual copied and pasted from the front page. How could you have used combinations to determine the second term only in p plus q to the power of 5? How could we have got the second term, 5p to the 4q, without having Pascal's triangle drawn the entire way out? Well, we're going to use these combinations to say there is some term in here in the expansion of p plus q to the power of 5, which would exist after the 5c0. There would be a 5c1. That's going to be your second term in the expansion of x plus y to the power of 5. So essentially, when I see that this is a power of 5, I know that this is my first part, my n of my combination. I also know that because I'm looking at my second term, I'm not going to choose 2. I have to choose 1 because my first term is a 5c0, and then it's a 5c1. So there's an easy little pattern we can try to push into our brain, but it might be a little bit challenging to remember. For the first term, we're choosing 0. For the first term, we're choosing 0. For the second term, we're choosing 1. For the third term, we're choosing 2. So we're going to choose 1 less than the term number. and this will again come up later and in the second part of our lesson. So how could we determine the second term in p plus q to the power of 5? We could say our power is a 5, and we are going to select the second term. We're going to choose one less, and a 5c1 is a 5. Now there's also the second part of this that says it's a p, and I'm pointing to it, p to the power of 5 first, and then it would be a p to the power of 4 next, and the q would be ascending from nothing to a q to the 1. So if we wanted to be even more perfect and talk more than the coefficient, we could introduce our variables p to the 4, q to the 1. A bit impressive considering we've never really been able to do anything more than a squared or a cubed with a bit of extra effort. So now's a quick one for you maybe to try. Could you expand a plus b to the power of 6? So you could look at your Pascal's triangle and ask what would be your next set of terms in p plus q to the power of 6. So maybe you build this up to say 1, 6, 15, 20, 15, 6, 1, and this is going to be our expansion in x plus y to the 6. So you may pause the video if you'd like, otherwise continue with our 1, 6, and I'll have to flip back, 15, 20, 15, 6, and a 1. Make sure I didn't miss anything. To the power of 6 means we should have 7 terms, 1, 2, 3, 4, 5, 6, 7, and it ascends and descends symmetrically, so we should be good. I know that this is an a to the 6 to start, and then an a to the 5, a to the 4, a to the 3, a squared, a to the 1, and a to the 0, followed by b to the 0, b to the 1, b squared, b cubed, b to the 2, or b to the 4, b to the 5, and 1b to the 6. Throw in some additions between those, and this is expanding using a bit of a pattern. Now again, we can use combinations to determine individually specific terms. And so what if we were to jump into something further than a to the power of 6 and ask specifically what's the fifth term in p plus q to the power of 8? To the power of 8, fifth term. Now there's a sequence of 9 terms here that we don't have written, and I'm specifically asking for the fifth. So we know that the fifth term means we should be choosing one less than 5. So we're going to be choosing 4. The power of 8 is going to be our n. So I'm going to go into my combinations to help me do this without having to build the rest of Pascal's triangle and say 8c4 is my coefficient, and then I'm going to have a p to the something. Now I know that it's going to be, to start, a p to the 8, and then a p to the 7, p to the 6, p to the 5, p to the 4, first, second, third, fourth, fifth term. I'm going to have a p to the 4, and then I know that my q's are going to ascend from q to the 0, q to the 1, q squared, q cubed, and a q to the 4. So p to the 4, q to the 4, this should generate for me our value. So as we grab our calculator and we number crunch 8c4, we end up with, again doing this in our calculator, 70 p to the 4, q to the 4, a very powerful final answer for the expansion of p plus q to the power of 8, focusing in on only the fifth term. So this is a little bit simple because we're limiting things to a p plus q or an x plus y or an a plus b, and not all binomials are this simple. So we're going to step this back a little bit and talk more about a cubing, but this time we're going to introduce a 2x and see how that changes things. So we've got a 2x plus y all cubed, and we're going to use first the Pascal's triangle pattern to make this simpler. So many people on the corner of their page will just say 1, 1, 1, so to the power of 0, to the power of 1, to the power of 2 to the power of 3. So this is a level of Pascal's triangle we're looking for. Our coefficients are 1, 3, 3, 1. And then we're going to have our first part of our binomial to the power of 3. And this is what's new. And then we have our first term of our binomial to the power of 2, and then to the power of 1, and then to the power of 0. We have the y to the 0, and then a y to the 1, and then a y to the 2, and then a y to the 3. Add these together, this is your result. This does tidy up slightly, but we do have a 1 times a 2x times 2x times 2x, or an 8x cubed. We then have a 3 times a 4x squared, or a 12x squared y. And for the first time when we talk about our coefficients, we see that the 1, 3, 3, 1 is impacted by having something more complex than an x and a y. So our actual coefficient becomes a 12. We then have a 3 times a 2 x y squared and a y cubed. And this is now expanding, still using Pascal's triangle, but expanding it where our binomials are more complex than an x and a y. There may be one for you to try and pause the video. Otherwise, we'll finish off try 2, an expansion of 2x squared minus 3y all to the power of 3 before switching to a new video which will expand on the idea of using combinations and introduce a formula for the binomial theorem. So our expansion of a cubic function still has our coefficients of 1, 3, 3, 1, but this time our first term in the binomial is a 2x squared, which is cubed. And then we descend a power to a 2x squared to the 2, a 2x squared to the 1, and a 2x to the power of 0. And lastly, we have a negative 3y to the power of 0, a negative 3y to the power of 1, a negative 3y squared, and a negative 3y to the 3. Being very, very careful here as we expand this that we're saying 2x squared times 2x squared times 2x squared, or 2 cubed is an 8. X squared cubed is a 2 times 3 power of 6. In the middle here we've got a 3 times a 2x squared squared times a negative 3. So being very careful and doing this one step at a time, we're going to have a 3 times a 4x to the 4 times a negative 3y plus a 3 times a 2 times a negative 3 squared, or a 3 times a 2x squared times a positive 9y squared plus a negative 27y cubed. So let's just tidy this up slightly and get to a final answer. 8x to the 6. There is going to be a subtraction of a 3 times 4, 12 times negative 3, negative 36x to the 4y, plus 3 times 2, 6 times 9, 54x squared y squared, subtracting a 27y cubed as a final expansion of 2x squared minus 3y cubed. So as we continue with this in our next video, we have a build on top of this to have higher powers, more complex binomials, and perhaps asking very specific questions about individual terms. A bit of practice from page 542 to get this going before we move on to a formula for the binomial theorem.